I'd like to welcome the next keynote speaker, Subramani Subi Kengeri, Vice President, AI System Solutions Applied Materials. The keynote is titled Heterogeneous Integration in the AI Era. A few words on Subi. Subi Kengeri joined Applied in March 2020 to start a new initiative, AI System Solutions. His team is chartered with the goal of architecting differentiated AI systems leveraging Applied's fundamental innovations. Prior to joining Applied, Subi was the CTO and Vice President of Worldwide Client Solutions at Global Foundries, responsible for enabling differentiated SoC and system solutions. Subi joined Global Foundries in 2009 as the Vice President of Global Design Solutions, responsible for worldwide design engineering and semiconductor ecosystem development. He was responsible for determining technological feasibility, competitiveness, and manufacturability of technology platform through cross-functional collaboration of customers, R&D, and ecosystem. In the role of Vice President of CMOS Platforms Business Unit, Subi was responsible for business results. He started his SoC design engineering career at Texas Instruments in 1991, and prior to joining Global Foundries, he was Senior Director of Design Technology Platform and Head of North America Design Center at TSMC. He has been granted 47 US design engineering patents and has given over 100 invited talks and press interviews. Please welcome Subramani Kengeri.
Kind introduction, appreciate it, and good afternoon, everyone. I'm really honored to be here in this major design and verification conference today. And first of all, I want to talk a little bit about our company, Applied Materials. Perhaps this is the first time Applied Materials is really coming in into a design and verification conference anywhere in the world. And you may be wondering why we as Applied Materials, who are essentially focused on enabling the semiconductor industry technology, is in a design and a verification conference per se. The world is changing, and we'll talk a lot about that. And before I go into more details on that, like I said, first of all, I want to give a quick overview of Applied Materials, a corporate intro for many of you who may not know. And then we'll talk about heterogeneous integration. Where are the challenges? Where are the opportunities? Why and how it makes a difference in system design and verification. You heard all day, including Lokesh, who spoke about some of the challenges in verification. And most of the other speakers also touched upon verification and the AI and ML aspects. So we'll touch on that as well. So, who are we? Applied Materials is world's #1 semiconductor and display equipment company. As an equipment company, an equipment and materials company for that matter, we have to stay ahead of the semiconductor industry to enable the rest of the world, the rest of the technology. So when we talked about Moore's law that was scaling for about 50 years, and it's continuing to scale, but kind of slowed down, we are at the forefront of enabling that technology and the node migration and the complexity of the monolithic designs and so on and so forth. We are about $23 billion in revenue, but more importantly, in terms of the R&D, we spend a significant amount of dollars, roughly $2.5 billion every year in R&D. And we have close to 16,000 patents, and we're about 27,000 employees worldwide. That's who we are. Our innovations, like I was saying earlier, is really critical to ensure that the technology scaling continues and Moore's law, continues to stay on track. Now, we all know Moore's law is slowing down, and that is kind of what is giving us and all of us an opportunity to look into newer areas to innovate, right? And we are trying to accelerate the innovation, which has been the fundamental mantra of the company for 50 years. We want to accelerate innovation, and we focus on collaborating with our ecosystem and our customers and their customers. So we understand the high value problems and try to solve them well ahead of the need. And then essentially, like I talked about the technology roadmap, the world is moving from a monolithic, litho-scaled technology roadmap to a heterogeneous integration technology roadmap, which we'll talk about, and so on and so forth. Now, we have been talking about the PPACT, which is we added the T, the small T at the end of it. PPAC was kind of known in the industry. All of you have been talking about it for a while. But adding the T changes your mindset. You got to do all of this with with a lot of focus on time to market. That's really critical. Then some of the previous speakers showed similar charts, but this is really, really important because this is the basis for a lot of our discussion. There was the mainframe era, there was a PC era, there was a mobility era, but now we are talking about the AI era. If you look at people talk about $1 trillion in semiconductor market or semiconductor business. The timeline is questionable. People talk between 27 and 2030, it'll happen sometime there. But let's take roughly $1 trillion of semiconductor business. Today, at $550 billion of semiconductor market, we are enabling the world GDP of roughly about $103 trillion. So in other words, there's roughly about 200x value that is created through semiconductors, which we may or may not realize, but semiconductors is at the heart of any technology in the world or any economy or any industry for that matter. Even if you look at agriculture to space, there is going to be electronics. So when this is such an important aspect and which was continuously driven through the self-fulfilling prophecy of Moore's law, if something slows down, if something gets impacted in terms of the technology scaling, the world is going to take it really, really seriously. And that is what drives the innovation of the next generation. And that's really what we should be talking about. So, right, starting from the first speaker all the way, we talked about AI and ML. The way to look at this is there are challenges in AI systems engineering. We can't talk about all the different applications and markets in the short time, so we're focusing on the AI and ML, which is a very important area, an emerging area, a growing, fast-growing area. We all know that. So if you look at the challenges, and you look at the models, and you look at the algorithms, and look at the requirements, and then look at where the memory and the I/O bandwidth is growing, there is no match. Things are completely out of control. The requirement versus what is available in the industry. Similarly, there are technology challenges, right? When we look at the litho-scale technology, it is slowing down. You're not getting the same benefit from a litho-scale technology as we used to get in the previous generations. So the node migration has kind of slowed down, and the benefits that you would typically get from a node migration is kind of slowing down. So with all that, it can significantly impact our future growth if there is no further innovation or if there is no solution. So the whole industry has been seriously thinking about this for a very long time. We all know in our lifetime, at least in the last about 20 to 25 years, Moore's law was dead at least 3 or 4 times, as far as I know. But it didn't really die. There was innovation. Necessity is the mother of invention, and there was more and more and new innovations. The litho scaling, we went from single patterning to double patterning to triple patterning to EUV to whatnot, and that's continuing to grow. All that was great. But in the recent past, things have definitely slowed down. There's no question about it. When we say it has slowed down, it simply means that you're not getting the same level of benefit from a node migration as we used to get in the past, right? And that has been now well accepted by the industry. And one of the things that happened somewhere in the middle of last decade, around 2016, is the industry started looking at the heterogeneous integration roadmap as opposed to a monolithic technology roadmap. That's a big deal. When ITRS, which was kind of the industry standard in conjunction with SIA, was the de facto industry roadmap, everybody would refer to that looking ahead for the next 15 years, and in some cases all the way to 20 years, has now abandoned the lithoscaling roadmap and now talking about HIR, heterogeneous integration roadmap. If you think about it, it's a big deal. And specifically, the lithoscaling, which you see on the left side, very focused on Moore's law. And then beyond 2015, it's about heterogeneous integration scaling. And that is focused on systems and applications. You have to think about the heterogeneous integration from a system perspective. That is really what's happening in the industry. So that's a big difference. When we're talking about the technology roadmap that is being scaled on a monolithic design through lithoscaling and the rest of the scaling, of course, that could have been done from a semiconductor aspect, from a design point of view, from a technology and a material point of view. But when you start looking at heterogeneous integration and that becoming the standard, you have to move up the value chain, or you have to look at from a system level if you want to be able to optimize the whole solution. So I request all the previous speakers, when we talked about verification or even some of the design challenges, system verification, system level architecture, system level partitioning, system design, system level trade-off is going to become more and more important, and solutions will be needed sooner than you think. So if you look at the opportunities in the AI era, if you look at what is on the y-axis here, there are different use cases and different workloads. And what is on the x-axis is the different parameters, different metrics. I won't go into the detail, but to take one of the examples here, one of the challenges is, if you take, for example, the processing per watt on the third column, and the bigger the bubble, the more important it is for that specific workload. You will see that when you look at face detection or when you look at some of the other real-time applications, the previous speaker kind of touched upon that. When it is real-time applications, the performance is going to be really critical, but it doesn't mean performance at any cost. You got to have performance with the right energy efficiency. So those things need to be considered very seriously. This is a good matrix to see different workloads versus different matrix. But I'm not going into the details of heterogeneous integration. I assume everybody knows what is heterogeneous integration, but I'll talk about some of the challenges and the roadmap and the issues. So heterogeneous integration comes in two flavors, right? One is the die disaggregation, which is, as you all know, when the die gets bigger and bigger, it is going to be very difficult to yield. And that's one of the reasons why the cost is really going up. So the cost per transistor is being looked at differently now. Instead of cost per transistor, look at cost per function, right? That's what is going to become more and more important. How you get that cost per function through integration in different ways, it doesn't matter, because the end customer doesn't care. They're really not worried about cost per transistor. They're really worried about cost per function. Having said that, what the die disaggregation becomes really important, because I hope you all know this. I'll say it in very simple terms. If you take a, let's say, 600 millimeter square die, and let's say there are 16 cores in it, okay, CPU cores, and so you're talking about 600 millimeter square. Because of the defect densities, they're just physics, there's nothing you can do about it, you're going to get a certain cost, certain yield, and therefore certain cost. However, and I'm talking about on the bleeding edge technologies, okay, 5 or 3 or the next node. And then, if you break it down to 4 pieces, let's say you have 150 millimeter square, and whatever number of cores you can put there, instead of 16 cores, you put 4 cores each. Then, the 150 millimeter square die, D0 is going to be far better. You're going to yield much more. So you combine that, and you make it work and get the assumption here is you get the similar performance, which you can make all that happen through proper optimization. Then your cost can be much better because you're going to yield much better, and you're putting it together. Therefore, the cumulative cost or the overall cost or the aggregate cost can be much better, and that, depending on the application, depending on the technology node, it could be anywhere up to 30% of die cost benefit, which is a big deal. That will put us back on the Moore's law trajectory, at least to some extent. So that's the die disaggregation. But then the other heterogeneous integration is, as you all know, there are certain functions that are optimal in certain technologies, right? RF technology, you want slightly older nodes, mature nodes, because you want the VT mismatches to be really, really good. And RF performance is all about, and analog performance is all about VT mismatch. And then you want a slightly older node. When you go to high voltage, you want a much, much older node. When you go to memories, you want a different voltage node, technology node. When you go to non-volatile, you want a different. But when you are looking at pure logic, and if it is at the heart of the performance metric, then you want the most advanced node. But how do you bring all those things together? The right way to do it is, like in the past, there used to be a system on a board. You take the discrete, chips manufactured in different technologies, bring them together on the board. But the world is moving from there to system on a package, right? System on a package is not new, but the way it is moving into the next era is very, very different. And we'll talk a little bit more about that. So you take all of these chiplets, if you want to call it, and put them together, not on a board, but on a package. That gives you a significant amount of advantage, and that's how the heterogeneous integration is going to really help going forward. So you can put in diverse component that I just described. You can optimize it, optimize the functions for those respective technologies. You get your die disaggregation benefit, and more importantly, you can go much faster to market. That is the T that I was talking about, PPACT. You can go, because you can reuse a big portion of that. For example, if you already designed PCI, or let's say some of the IOs, you don't have to redo it when you go to the next node. You only go focus on getting the most advanced CPU core in the most advanced technology node. The rest, perhaps, you can reuse to a large extent. So that's the difference between a monolithic design, which is really, really expensive, huge amount of investment. I heard $1 billion earlier. It takes much longer time. Whereas if you break that down and say, I'm going to focus on the CPU core or whatever the most critical one is, but the rest I'm going to reuse and put that on a package and still get a significant amount of next generation performance per watt or whatever the metric be, then that has its own benefit. So that's where the heterogeneous integration is going to become more and more important. But at the same time, not everything is simple. If you look at the challenges in the AI era, one of them is the workloads are going to be very different and for different use case and different applications. But you won't be able to build custom designs for each of those workloads and applications. You may almost need a fully configurable but fully optimized solution. You want the flexibility of a full configurability, and you want the performance of a custom. It's not easy, as we all know. But with heterogeneous integration, when you integrate the chiplets, if you have all the right chiplets and you have an inventory of the right chiplets, you will be able to plug and play and create workload-specific chips and solutions much sooner. And that's going to be the next generation. That's where the world is moving towards. That's really the key message there. Having said that, advanced packaging is going to be one of the critical technologies in the next generation. I think it's obvious from everything I was just saying. All these things are going to be not necessarily on a monolithic silicon, but it's going to be on an advanced packaging technology and advanced packaging substrate. Anything that can be done to improve the value of the overall system using advanced packaging is going to be the next technology enabler and a critical enabler. The whole industry has restarted the innovation engine on packaging technology. If you see TSMC, they recently invested about $10 billion in packaging technology, 10 billion. They're going to go continue to do it. Intel has announced multiple advanced technologies for their IFS. Everybody's looking at how to take care of this and how to solve this problem or using the advanced packaging technology. And you see the technology, the packaging technology scaling in the limelight going forward. Now, having said that, one of the important aspects of heterogeneous integration at the system level is going to be what we call a system technology co-optimization. If you really want the right performance, if you really want the right architecture partitioning, the performance per watt, and everything else, you have to be able to optimize from the system level at every layer all the way down to the technology. That's what you see on the left side here. You start with the use case, look at the hardware and software data flow, because if you're going to mix and match different heterogeneous cores, how will the software be able to comprehend all of that? How can you take care of that part? Has to be looked at up front. And then you look at the architecture trade-offs, and I'll show you some examples of some of the things that we have done. And then the advanced packaging and all the way to the materials. On the right side is all of the kind of a fishbone diagram, but you can see all the inputs that are going in. You need to look at the compute engine performance. You need to even look at algorithms. If you can, I'll tell you why that is also important. How can you optimize your memory subsystem? Because a big portion of the monolithic design is now on the package, right? And then you have to look at the package lithography. When I say package lithography, I simply mean in the front end, which is on the silicon, the technology scaling has improved. You've gone from microns to nanometers, and you continue to do that. But on the package design, it is at least about 20 to 30x larger compared to a front-end silicon. I'm talking about the line space pitch and the VR pitch and interconnects and so on and so forth. But you need to go innovate there and be able to get much better line space and better pitch on the substrate, on the package, but that's not easy simply because of physics. And we'll talk a little bit about that as well. My point is, you need to be able to look at all of these various inputs and look at the trade-offs if you want to extract the best value from heterogeneous integration. Some of the examples are something like this. When we talk about the co-optimization, this is kind of framework here. You look at the use cases, you look at what AI frameworks, I'm again focusing on AI and ML here, and look at the compilers, look at all the way down to all of the hardware aspect. When you do things like this, and then if you can optimize your data set, because a big portion of the data is going to be communicating on the package. So if you can, optimize your I/O bandwidth, okay, then it's going to improve your energy efficiency and of course the cost as well overall. So if there are ways to do that, and some of the ways that we have been doing it, our team has been very focused on this, is how can you reduce the I/O bandwidth for specific workloads? On an average, this is again a high-level average for different, for example, image recognition would have ResNet 50 and many other workloads. But then if you take an average, you can save about 35% bandwidth just through optimization. If you can do that, it'll help in the heterogeneous integration. The other way to look at this is when you look at maybe an example of a different type of a client SoC or whatever you want to consider this to be. If the CPUs and the GPUs and the NPUs and the last level cache are all disaggregated versus putting everything on a monolithic silicon, there are a lot of challenges. Because those lines that you see, like a 20 nanosecond and so on and so forth, are now running on a packaged substrate, not on your most advanced silicon. You have to consider those aspects. So therefore, the packaging technology analysis, verification, is going to become more and more important. Your optimization there is really important because if you take an example, the chart at the bottom right that you see, is there a laser? Okay. It's okay. If you look at the bottom right and you have the graphs there, you see different workloads. This is for the spec CPU, the whole integer suite. And if you see the breakdown here, what you see on the x-axis is a percentage of performance degradation for every 1 nanosecond of latency. When the signals are now running on the package, some of the critical signals versus on the monolithic silicon, it's going to be slow if you're not careful, if you're not optimizing the whole set. So in 1 nanosecond of that delay will, or basically latency, will impact the performance of the CPU up to like 0.4%, depending on the workload again. And that is really something you should know upfront while you're designing, while architecting. This would not have been the same if everything, including the LLC, on the same monolithic design. So this is why the world is changing, the way it needs to be architected, the way STCO works, or the system technology co-optimization, is going to become more and more important. And therefore, all the EDA tools to take into account some of this analysis, some of the design, some of the verification at that level is going to become even more important. Another quick example is when you look at the memory subsystem, which is of course a very critical piece for any of the applications, you have to be able to optimize it. Now, if you lost some of the latency or the performance because of the previous chart that I showed you, because the signals are now running on the package versus on the monolithic silicon, you have to be able to compromise or offset or optimize it. And there are many different architectural trade-offs. But if you look at, let's say, increasing the cache size, what does that do to your latency and your cache hit or cache miss, whichever way you want to look at it, cache efficiency for that matter, in different workloads, all that has to be looked at if you want to really get the most advantage. So the whole world is changing in terms of the design, the architecture, the trade-offs, the optimization, and the implementation from a monolithic world to a heterogeneous world. That is really one of the key points. Having said that, when you put in different architectures on the same system, if there is a need for it, x86 ARM, let's say RISC-V, heterogeneously integrated, or different GPUs. The GPUs can be maybe a very low power GPU for certain aspects, for very, very high performance GPU for certain other applications. Everything on the same package, everything on the same package. When you put in all those and it's coming from different sources, let's say different vendors, you have to make sure the software is going to be fully optimized. That has to be thought through upfront as well. So integrating all of that, the world took about 20 years or maybe a little longer to perfect the monolithic design in terms of EDA, in terms of system architecture and all that. Now we are going to the next level. It's not completely new, but you'll be able to reuse a big portion of all the R&D and the work that was done in the last 20 years from monolithic to heterogeneous. But there are a lot of gaps. If you look at all the EDA tools, which is why I wanted to stand here in the DV conference and tell you all that since the world is moving, it's not completely new, but I wanted to give a specific focus and talk on why this is important. And there are going to be gaps in the EDA tool set going forward if nothing new is done. Then in terms of the heterogeneous integration, packaging challenges, all those things that we talked about are the design and the software aspects. But when you get to the packaging, there are going to be new challenges as well. Because when you get to heterogeneous integration, the sizes are going to be much larger. There are going to be multiple chiplets. Bringing all of them together on a large substrate has the warpage issues to the bandwidth and the I/O issues, because you want very high speed signals now running on the package versus on a bleeding edge technology. That forces the designers to start looking at the signal integrity and power integrity in a much more sophisticated way. Unlike in the past, it was not, unlike in the monolithic designs where things were very short runs for that matter, in a few millimeters, and you would optimize it, and there are ways to do that. But now the signals are going to be running. Critical signals are likely going to run on the package and much longer distance, and that poses a lot more signal integrity challenges. So that has to be looked at. Similarly, on the thermal and the power and the performance optimization is also going to be some new challenges there. Thermal, because you're going to have multiple chiplets spread out, of course, that helps power density to some extent, but each one of them will be burning power, and then you have to take into account what that does to your overall thermal management, your integrated voltage regulators in terms of the power integrity, and then the thermal aspect of it. You have to study all of that upfront. Similarly, on the warpage means, as you all know, the substrate can bend because of just the physical properties of the organic substrate. And then you have to take into account all of that upfront. That makes a big difference. Now, here is the fine point. When you have a large monolithic die, the warpage is going to be X, let's say. But when you have multiple chiplets spread out, it contributes to warpage in a different way, because the utilization, the breaks, the gaps, all of that makes a difference. So that has to be understood thoroughly. And every placement, every layout, every floor plan of the chiplets can cause different issues and different challenges if you're not careful. How do you verify this? How do you simulate this? How do you verify this? How do you make sure you got it first time right? Requires very sophisticated EDA tools to make sure that all of these things can be emulated upfront. Having said that, when you have those chiplets and when you place them, when you have multiple chiplets, it's almost impossible to get it right with 100% alignment for every chiplet. There will be some displacement, there will be some turns, there will be some dislocations. That can cause yield problems if you're not careful. If there are EDA tools that can look into upfront and try to assess this and simulate these, then you can get it first time right. So that is almost the end of my talk. I wanted to give a flavor of the world moving from monolithic to heterogeneous, where the challenges are, in particular for the AI and ML era and the applications. There is definitely going to be a lot of challenges. Everybody wants more compute power, and we all want cost efficiency, and therefore the new generation of the AI hardware solutions, not the one Newman architecture, but new architectures are coming up. And there are going to be cloud and edge computing. Some of the previous speakers also touched upon that. That will call for new silicon architectures. You need faster insights, and some innovation is needed there. And advanced packaging I talked about. And at the end of the day, new architectures are going to come into existence. Having said that, I'll end this with what our CEO has the vision of making sure that we as leaders really leave the world in a better place. So we got to take this, be a part of the innovation journey, be a part of the trajectory that takes the world to the next generation, help and support. So that's our CEO there, and we're all working towards his vision of what he wants to do in the next 5 to 7 years. We see the world changing, and we want to be at contributing and enabling as a leader. Okay? Thank you very much. Appreciate it.
Thank you so much. In the interest of time, we'll take just a question, single question. Okay. Anyway, we have a 10-minute break, so you can catch up with Mr. Subramani during that.
Thank you very much.
Just a minute. I'd like to request Pradeep to hand over a token of appreciation to Subramani Kengeri.
Thank you very much. Thank you.